All right, my name is Hossein Sheikhi Darani, and during this presentation, I'm going to talk about the project titled the Autonomous Vision-Based Navigation for Quadrotor using Deep Reinforcement Learning. And before going on, I would like to mention that this project was done as part of our machine learning course at SFU at winter 2020. I think the title itself is kind of self-explanatory, so let's start with some motivations. You may have heard about the Alpha Pilot Challenge. It's an autonomous drone racing challenge. There's a racetrack and there are some gates on the racetrack. The robot has to start from one end and goes to the other end as fast as possible while going through these gates. In 2019, a team from RPG Group at ETH achieved the second place. You can see their system design pipeline here. The idea of our project is inspired with their system design, and we came up with the idea of replacing their state estimation as well as their planning and control module with a deep reinforcement learning agent while keeping this perception module. To do our experiment, we chose the AirSim simulator, and in the right-hand side figure, you can see a top view of a simplified scenario. A drone has to start from one side of the room and goes to the other side as fast as possible while passing these static objects. Within this project, we evaluated the deep DQN and two of its variants. And in each state, the robot can choose between going forward, rotating toward the right, or rotating toward left. And we designed our reward function somehow that encourages the robot to go toward the goal as fast as possible with less possible actions. The tricky one is about our observation space representation. You can see at the very right side of this figure that the observation is a 100 by 30 pixel depth image, which includes two different parts. The first part is showing at this bottom middle part. It's a depth image, which by size 100 by 20. Our experiments validated that we do not need the whole forward-facing camera because there are some extra info, for example, the ground or the ceiling, that are not necessary for the agent. So we just simply cropped a narrow image from center of the forward-facing camera. And on the other hand, we have this tracking bar, which is the 100 by 10 pixels. It's a black horizontal line with a white square located in it. And the white square indicates the relative heading of the robot toward the goal. And we assume that this information, the information that is provided with the tracking bar, is obtained from that perception module that we kept in our system design. So there is a some gate detection algorithm that gives us the relative heading of the robot toward the goal, and we use it to enrich our observation data. You can see our experiments results here. The left figure is showing the accumulated reward in each episode, and you can see that the best results are coming from blue and green. But because it's a race competition, it's a race scenario, we should consider the duration of each episode as well. So you can see that the better results are coming from the blue, which is a double dueling DQN algorithm. Our project demonstrated a promising result when enriching the raw sensory observation with some extra info. I'm talking about that tracking bar, which its information are obtained from the perception module. And we showed that just a narrow crop of the whole forward-facing camera is sufficient, and it will causes the faster training than feeding the whole image. And our training and testing results shows that the double dueling DQN has a better performance in comparison with DQN and double DQN.